we have discussed earlier on our previous class, the equivalent circuit of transformer. Here I have drawn the transformer where both sides have each of their elements. Okay, and then we're gonna discuss the refer to side, right? Refer to primary side, or refer to high voltage side, or refer to low voltage side. Okay, so basically here I have drawn the equivalent circuit for both the sides. Okay, I'm going to discuss each of the parameters here. Okay, so basically this is R1, this is the resistance of our primary side, and this is the R2, this, sorry, okay, R1, this is our resistance from the primary side, R2, this is our resistance from the secondary side. Okay, but basically I would prefer referring rather than primary or secondary, we should refer these like high voltage side and low voltage side. Okay, it makes our calculation much more easier, and understanding the circuit would be much more easier. Okay, then there's some this reactance. This is the reactance that comes from the coil of high voltage side. So this one is X1, the reactance, and this one is X2 that comes from the uh, coil of second low voltage side. Okay, then basically there's two important parameters. One is resistance that represents our hysteresis and eddy current loss. Okay, as you know, the loss is a real power, so we need to consider this resistance because of the loss, because that's the real power. We need a real component to model that. And for the leakage flux, we modeled and reactance, a reactance like Xm. Okay, so here as you can see, the high voltage side voltage is V1 and low voltage side voltage is V2, and we have considered our turns ratio A as V1 by V2. So the final equation, the total equation, ultimately we can see that I2 by I1 equal to N1 by N2, their turns of respective sides. Okay, so as I have mentioned earlier, this is the equivalent circuit where I have considered both the sides. What happens when we consider this equivalent circuit from one side rather than considering both the sides, right? So let's see if we consider this equivalent circuit from our high voltage side. Okay, so here I have drawn our equivalent circuit referred to high voltage side. So as you can see, we have moved our hysteresis and eddy current loss, resistance and magnetizing reactance block to left side. We have changed the position of our block parallel path that consists of hysteresis and eddy current loss and magnetizing reactance. Okay, because the I naught current is so small that it doesn't affect the current on this path, so we can move freely this parallel path. Okay, so then finally we can see that the high voltage side resistance R1 is as it was, X1 is also the high voltage side reactance, so it doesn't change, but the low voltage side resistance that is now referred to high voltage side is a square time multiple of its original value, and same goes for the reactance, and same goes for the load that was on the low voltage side. Okay, so that's how we can transform or refer our total circuit of transformer to high voltage side. Okay, so the currents and voltages are also mentioned here, as you can see. Now we see the equivalent circuit which is referred to the low voltage side. This will be quite similar like the high voltage side, but high voltage side is impedances will now be referred to the secondary side by multiplying 1 by a square. Okay, by simply multiplying 1 by a square, so the resistance, the reactance, we have to um, multiply 1 by a square to the hysteresis and eddy current loss resistance and also to the magnetizing reactance. So this is basically the combination of both referred to high voltage side and low voltage side equivalent resistance. We will be using this for many of our applications in our uh, course. Okay, now we need to discuss about the phasor diagram of transformers. So here is our equivalent circuit, which is referred to high voltage side. Now if we use a simple KVL on this side, okay, if we use a simple KVL on this side, we get this equation. Okay, where is V1 is equal to I1, you get it. So finally we consider this R1 plus A square R2 our R equivalent, so simply as we can see, and for the reactance also. Okay, so this is basically our final equation based on which we'll draw our phasor diagram. Okay, so first we can see our phasor diagram for lagging power factor. So lagging means current lags behind it, here voltage. Okay, so here we consider our AV2 as reference. So we'll be drawing our total phasor diagram based on this reference AV2 as our considering as a reference. So basically, as you can see, we have taken our AV2 from the equation. As you can see, we have taken our AV2 as our reference. So this is our reference line. Okay, then comes I1 R equivalent into. So I1 is lagging. We have shown I1 here and theta lagging. So theta is negative. As we all know that resistances don't contribute any phasor, so they will be the same as I1's angle. So as you can see, the blue line and the green line, they're both parallel to each other. Okay, then there comes this J I1 X equivalent. As there's an imaginary part here, we know that if we have any imaginary part, the phasors will be shifted towards 90 degree. Okay, so as you can see here, our J I1 X equivalent, which is 90 degree shifted from our phasors of I1 R equivalent. So as you can see, our final phasor will be V1, which will be from the initial point to the end point V1. Okay, so this is our phasor diagram for lagging power factor. So the same equation we will be using for leading power factor and unity power factor. So here, as you can see, our leading power factor, our phasor diagram will be like this. So this is our reference AV2. Okay, then I1 are equivalent, which will be parallel to the angle of I1, as you can see. Then this JI1X equivalent, this will be 90 degree with I1 are equivalent. So finally we draw our final result V1, which okay. Now for the unity power factor, the phasor diagram is much simpler here. As unity, the power factor is unity, you know, the angle will be 0 degree. Okay, the simply angle will be 0 degree. Okay, so this is our reference AV2, and the current will also be on the same direction. So as the current is on the same direction, I1 R equivalent will also be on the same direction, and J I1 X equivalent will be 90 degree with that line. Okay, so finally we draw our V1, the final voltage, the resultant voltage that we want to see. So basically this is the three different power factor phasor diagram for transformer that we have studied.